Now, what are these equations? The energy of the battery, CVB squared 1 minus e to the minus 9, the energy dissipated in the resistor, the energy dissipated in the capacitor. How can we derive those based on what we just derived? So all these are derivable simply by getting these equations that we have for the charge and manipulating them or differentiating them. So for example, if I wanted to show how does the energy stored in the capacitor change as a function of time? How does the energy produced by the battery change as a function of time? How does the energy dissipated in the resistor change as a function of time? And then how does the energy produced in the capacitor, stored in the capacitor, change as a function of time? So the capacitor would be pretty easy because the capacitor equation is just half CV capacitor squared. So I already know the voltage of the capacitor is this. Yeah, that's it. So it's just basically energy of the capacitor is 1/2 C, and then that equation squared. Okay, so then you just have here VB squared 1 minus e to the minus t over RC squared. That was very quick to derive. Let's see, is that the equation that we have on the formula sheet? That's this one right here. Half CVB squared minus e to the minus t over RC squared. Yeah. Okay, the next one we can calculate the energy of the battery. And then for the resistor, we can subtract these two to get the resistor. It's easier that way. So for the energy produced by the battery, I could say voltage of the battery times the current in the circuit. No, not that. That's the power. Yeah, okay, hold on. Let's see. The power of the battery is the voltage of the battery. Why don't I just do this way? We could say the energy of the battery is half Q times voltage of the battery. Oh yeah, that's it. Yep. So the charge that's flowed, so as a function of time, the charge that has flowed through the battery, and then the voltage of the battery, since that's constant. And then so we use the equation for the charge as a function of time. Okay, so let's see here. Half, and then this is going to be the Q equation that we have. It's the Q equation. It was on the other page. CVB 1 minus e to the minus t over RC times VB. Yeah, that's it. Energy of the battery half CVB squared. So it kind of looks like this. The energy of the capacitor. This is the energy of the battery, CVB squared. And then you get here this, but without the square. 1 minus e to the minus t over RC without the square. So this is the energy produced by the battery. And then the energy of the resistor should be their difference. So whatever the energy of battery you're producing, remember what we said, that the necessary evil is that when you're charging the capacitor, the charge, some of the charge, the energy has to be lost in the resistor. So, so when you subtract these two, this minus this, half CVB squared 1 minus e to the minus t over RC minus 1/2 CVB squared 1 minus e to the minus t over RC squared. Right, so then you can factor out this one, factor out one of these, then you get the energy lost in the resistor is going to be half CVB squared is equal to 1 minus e to the minus t over RC. 1, when I factor this out, you get a 1 minus one of these, 1 minus e to the minus t over RC. And now you have to take, cancel this. So you basically get energy of the resistor, half CVB squared, and this cancels, and then this turns into a positive. Then I could take this, put it in here, minus e to the minus 2t over RC. Okay. So then you're going to have here, let's see, is that the equation we have? Energy of the capacitor, 0.5 CVB squared. Oh, no, sorry, the resistor, 0.5 CVB squared. Yeah, this is wrong for the energy of the battery. This doesn't give you the accumulated energy that the battery has produced. It gives you, the half gives you the instantaneous energy that the battery is supplying at any particular instance. We want to know how much energy the battery has supplied from t equals to 0 to some time t. So the better way to do it would be to say the power of the battery is voltage of battery times the current in the circuit. And then the current in the circuit is going to be VB over R e to the minus t over RC. Oh, you have to be careful. Yep, that's the better way. So the power of the battery is VB squared over R e to the minus t over RC. Then you say the power of the battery is the rate at which it's supplying energy. Then you integrate this. So du is equal to VB squared over R e to the minus t over RC dt, integral from 0 to some time. And then when you do this, you don't get the half. You get the CVB squared without the half. That's weird. So yeah, U is equal to VB squared over R. And this is going to be RC e to the minus t over RC, 0 to t. R and R cancel. Oh yeah, CVB squared, 1 minus e to the minus t over RC. Oh yeah, exactly. No half. So like, for example, here, you see the power of the battery is voltage of battery times the current in the circuit. So it's better to derive this and then integrate that to get the energy produced by the battery up to some time as a function of time. For the capacitor, it's better to calculate the energy stored in the capacitor to get this first, then differentiate this to get that. So with the capacitor, it's the other way. You do this, the energy of the capacitor, using what we did, same thing that we did here, half CVB squared. Okay, you do half CVB squared, then you differentiate this guy and you get this. You see, that no, you don't get that. Oh, I haven't given the equation for the power of the capacitor here. I didn't write it. So what would that be? The power of the capacitor. If we differentiate this, you get the rate at which energy is being stored in the capacitors. Power of the capacitor, the derivative of this is going to be, the 2 is going to come down, CVB squared, and then the derivative of this is going to be 1 minus e to the minus t over RC, and then the derivative of the inside is going to be e to the minus t over RC times 1 over RC. And then the C and the C is going to cancel. So the power of the capacitor equation is VB squared over R. And then this one multiplies e to the minus t over RC minus e to the minus 2t over RC. So that's the power. That's the rate at which you're charging the capacitors, the rate at which you're charging the capacitor in an RC circuit. So that would be, that you could put that here. For the resistor, you could do I squared R. Yeah, the best way to do the resistor is to do the power. So for the battery and the resistor, it's better to derive this guy, integrate it to get this. Derive this one, the power of the resistor is I squared R, and then do that, I squared R, and then integrate it to get this. Or you could just get this by subtracting these two, right? And then you get the energy lost in the resistor, okay? So now if we plot this, let's say, let's go back to our circuit. See here. Let's go back to our circuit of 10, 2 kilo ohms. What was it? 5 millifarads. So then what would the energy equations look like? The energy of the battery would look like what? It's CVB squared, 1 minus e to the minus t over RC. So then energy of the battery would be, this would be 5 millifarad. Voltage of the battery squared, 1 minus e to the minus t over, and then this would be 10 again. So this would be 100 times 5, 100 times 5, this is 500 millifarads. So yeah, 500, so millifarads, so then that's 0.5. So this is in joules then. This is how much energy the battery is going to store as a function of time. Okay, now let's plot that. In that circuit, so it's going to be the energy of the energy produced by the battery. (0.51 minus e to the power negative t over 10. Oh, maybe it doesn't like the, okay. The next, let's see here. I'll just copy paste here. This is the energy of the battery, energy of resistor, and energy of capacitors. So I'll do it like that. Battery, resistor, capacitor. I'll do it the same way that it's written in the formula sheet. .5 joules. Maybe it's better to graph this as a millijoule, huh? 500, yeah, let's just graph it as millijoule. 500 millijoule. Okay, so let's see here. Okay, so I'm gonna graph this as a 500, and this is millijoules. Okay, what's gonna be the equation for the resistor? What was our equation? That's probably the more complicated looking one, 0.5 CVB squared. So half CVB squared. So you could say two ways to derive this. One, get the power and then integrate it to get that, or just subtract the energy of the battery minus the energy of the capacitors. And then you get that. So then 0.5 CVB squared, 1 minus e to the, what was it? Minus, there's this 2t over RC, right? There's an extra 2 up at the top. Okay, so 1 minus 2t over RC. So it looks like that. So then this is half CVB squared, so it's going to be 250 basically. 250, 1 minus e to the t over 5. Okay, so 250, and this is also millijoules. So then that's, we can graph that on Desmos. So this one is the resistor now. Well, minus t over 5. Okay. And now the energy stored in the, let's zoom out here. Okay. So now we're kind of, the picture is taking shape. Okay, now how about the energy stored in the capacitors? What's that going to be? The energy is stored in the capacitor. What was the equation? Well, that was the first one we derived. It was half CVB squared, 1 minus e to the minus t over RC squared. Right, so it's going to be back, it's going to be to 250. 1 minus e to the minus t over 10 quantity squared. See, they all look different. So this is going to be 250. Oh. Wait. Let's see, how do I erase this? To the power 2? Is that right? No, I don't know if it did it. Yeah, I could just do it this way because they're going to multiply 2 of these. Yeah, like that. It's the whole thing squared. Ooh, so here it's, let's see here. There's three graphs here, right? So let's see here what's happening. This is the, okay, so this red one is the energy produced by the battery, right? And this one is the energy produced by the capacitor, I mean, stored in the capacitor. It looks like these two are in phase with each other. So in other words, as over time, the battery is producing more and more energy. And when you get to 10 seconds, it's produced 63% of it, the energy that it will produce, right? So the time constant is 10. You see, so then eventually at the end, the battery will produce 500 millijoules of energy, of which 250 joules will be stored in the capacitor. You see? So do you see what's happening here? Energy conservation, essentially. So when you connect the battery across an RC circuit, the battery is producing more and more and more and more energy, right? And eventually at the end, it will have produced 500 millijoules of energy. Out of that, 250 will go into the capacitor. Now, how much will go into the resistor? The resistor also plateaus into 250. Do you see what's happening? So half of the energy produced by the battery goes into the capacitor. The other half is dissipated as heat in the resistor. Half. So you can kind of say this machine is 50% efficient. You see, back to if you think about it like a heat engine, 50% efficient. So what should happen at any instantaneous time, let's say at 10 seconds or 20 seconds, if you take the energy of the battery, of the capacitor, is 186, right? So if you take the energy of the capacitor at 20 seconds is 186. The energy of the capacitor that you have stored is 186.911 millijoules. How much energy is lost in the resistor at 20 seconds? So just go up all the way to the red line and say, okay, at 20 seconds, 245 joules is lost in the resistor. 245. And now in 20 seconds, how much has the battery produced? Why does it do that? $432.332. So what should happen? So at any time interval, like if you take any X value, essentially, you say, oh, at 20 seconds, how much energy has been produced? How much energy has been produced in the battery, right? Is 432. How much of that has been lost to the resistor? 245. And how much of it has gone into the capacitor? 186. If you add these two, what should you get? Yeah, you see. So these two added always give you that, how much the energy of the battery was produced. So what's happening here from the graphs, it looks like initially the resistor is dominating. It takes a while for the capacitor energy to build up. So initially most of the energy goes into the resistor and is wasted, you know. But then the resistor reaches its peak right there. And after that, you're starting to charge the capacitor, and the resistor has already plateaued. No more heat produced into the resistor. Oh, that's kind of weird how that happens, why that happens. You see, the time constant of the resistor is 5 seconds. To really think about why that's happening, you know, it's a lot of it is coming from the derivatives and all of that, but to really think about what's happening. So out of the energy produced by the battery, initially most of it gets wasted. And then it's almost like the resistor reaches its plateau. And now the capacitor says, okay, I'm going to catch up. I'm going to catch up to you. And now they're both 248. And now when you add them, you get the energy produced by the battery. Wow, it's kind of weird. Maybe the answer to our question, why does the resistor reach its peak first in terms of energy, maybe the answer lies in graphing the power function of each of the three. You see? Take the derivative of this, take the derivative of this, take the derivative of this, and then you get these equations. The power produced by the battery, the power produced by the resistor, and the power produced by the capacitor. You see? And what would those three equations be? So the power, because the power is the rate at which you're producing the energy or you're losing the energy, right? So maybe the answer lies in the power equation. So what would the power equation look like? Power equation of the resistor is going to be what? Well, let's start with the battery. So that's going to be VB squared over R e to the minus T over RC. And then the power equation of the resistor is going to be VB squared over R e to the minus 2T over RC. And then the capacitor is going to be, what was the capacitor? I had it a minute ago. Oh yeah, it was VB squared over R e to the minus T over RC minus e to the minus 2T over RC. Well, essentially, once you know any two of them, you can say, okay, then this, subtract this from this, and you get that. So you don't necessarily have to derive it. So there's two ways to get this. Either differentiate this function, the energy of the capacitor, differentiate, where was it? This, I had it earlier. Oh, here, this, differentiate this equation, or just subtract these two to get that. Okay, so then what would that be here? In my case, the voltage of the battery is what? 10 squared over resistance is 2 kilo ohms. E to the minus T over 10. This is 100 over 2, that's 50. And I'm going to just record it as a milliwatt. And this is going to be energy of the power of the battery. So this is the power of the battery, the rate at which the battery is storing energy in the system. And this is the rate at which the the energy is being lost to the resistor. So it's 50 milliwatts e to the minus t over 50, 1 over 5. And then the power of the capacitor is 50 milliwatts, just this minus this. Oh, pen is dying. Oh no. Okay, so now okay, power of the battery is going to be 50 e to the power negative t over 10. Power of the capacitor. The power equations are easier because they don't have the 1 minus 1. So it's just, that's it. And then this one is just simply going to be, I'll just copy this. This minus this guy. Oh, weird. Look at that. Oh. Okay, so this one is telling you when t is 0, the energy of the battery, the energy of the battery is this top one, right? So then the energy, this is the rate at which the energy, the battery is producing energy. So it's going down, and then eventually it's not going to produce more. It's not, the rate at which it's producing is going to be 0. At the end, it's not going to be producing anything. It plateaus. And then this is, so you see why do you see why initially the resistor dominates? Because all the power that the battery is producing is going to the resistor, you see. The resistor power also starts high. Why? Because remember that initially the current is very high. As soon as you connect it, the capacitor is on charge, right? So the current is very, very high. When the current is high, a lot of heat loss in the resistor, you see? So the resistor's power, the loss of power in the resistor is very high, but it's dying. It's dying, it's dying, it's dying, you see, very quickly. So the time constant of the resistor is twice as fast. The power that's lost in the resistor is dying twice as fast. Now, what's the rate at which you're charging the capacitor? Initially, the capacitor's rate of change of power, the rate at which you're producing energy is 0. Then you're starting to increase. Reaches its max. When does it reach its max? 6.93. Then it goes to, then at the end, then you're producing less and less energy, but see, by then the capacitor is going to start to catch up. In other words, is this the same time when the capacitor oh, this is beautiful. This is, so the power is increasing, reaching the maximum power in the capacitor, then it's dying. So can you kind of see why eventually the capacitor catches up? because more of the energy produced by the battery, more of the power produced by the battery is now going into the capacitor. You see? Like that. Woo! Okay, so how can we answer, now that we kind of know a little bit about how these equations behave and what they mean, let's do an example here.